Okay, thanks for coming. My talk is devoted to construction which is called Zendoo. It's a verifiable protocol for decentralized and decoupled side chains. So how to do truly decentralized side chains. So I will speak about sidechains and their purposes, first generations of approaches, what risk do we have with them, what we have modern constructions of sidechains, what do we have with our solution, and how it works in fully-fledged operation, what solution, how we instantiate it, what is lattice sidechain, and what open questions do we have with sidechain research right now. Okay, so if we are speaking about sidechain, we have some main blockchain and we have several sidechains. We have classical interledger communication problem, how to make independent sidechains, independent blockchains to communicate each other, and how to do this communication secure and efficient. Why do we need sidechains? First of all, of course, we use this for cross-ledger communication. We need to connect different blockchains to each other. Besides that, we're solving a scalability problem. We have limits on transaction throughput, on information processing speed on each blockchain, and connecting blockchains together, we solve a scalability problem. Besides that, we add extra functionality. We, besides some traditional extra functionality like putting smart contracts in sidechains, putting treasury, governance on sidechains or something like that, we can also implement in sidechains registry of real estate, car registry, some commercial services, and so on. Everything can be put on sidechains and can be run more efficiently than in smart contracts. And of course, we can increase security of the main blockchain. If we remove complex component from there, like virtual machine and so on, we move such functionality into separate special intended sidechain for these purposes, we increase security of the main blockchain. We improve robustness of this solution. We have very simple operation. We have high hashing power or high stake participation here. We have high level of security, and all other functions is provided through sidechains. And of course, we improve decentralization and robustness of the whole solution because we have many sidechains, and if we have enough level of security, of course, we improve decentralization. So, if we speak about first generation approaches and risks that appear together with them. So, initially, sidechains were proposed in 2014 by Beck and his co-author in a paper with, which is called two-way packet sidechains. And two different approaches with synchronous and asynchronous communication between these chains. And then we had drive chains that work on Bitcoin. So what do we have here? We have Bitcoin blockchain and we have some sidechain, for example, rootstock. In Bitcoin, some Bitcoins are locked. They are sent to some multi-sig account, and after that, Bitcoins are locked here and they are sent to some multi-sig account. And after some period of time, they appear on this sidechain. They can transfer in this sidechain, they exchanged, and at some moment, owner of these tokens in this sidechain would like to send them back in Bitcoin, and he gets his Bitcoin back in the main Bitcoin blockchain. It seems everything quite okay, everything works quite smoothly, this is a good solution, but what potential problem do we have here? Here we have multi-sig account, here we have some federation, here we have some merge mining, and if something goes wrong with federation, it means that there will be problem for token holders in sidechain. So from Mainchain point of view, from Bitcoin blockchain side, owners of these Bitcoins are just this federation. If you trust this federation, if everything goes well with this federation, everything works quite okay. But if there is some incentive for federation to take this coin for themselves, to send them to another account, then it means ownership of such tokens means nothing because they cannot convert them to Bitcoin. This is the first generation of sidechains. What do we have now as sidechain solutions? Now we have a formal treatment of proof of stake sidechains. We have a paper that appeared 2 years ago. Besides that, we have a paper which proposes sidechain constructions that where the main chain doesn't know structure of sidechains. We have formal model for a non-interactive proof of works for proof of work sidechains paper. We have plasma-based smart contracts with sidechains by Poon and Buterin. We have Liquid, Polkadot, and other solutions. So there is very intensive development in this area. So what is our solution? We go to the solution when we have full decentralization and we have no federation and no any trusted party. So we keep this idea that there should not be any central weak point. There must not be any federation, and we must keep security level for all sidechains at the level of the main chains, having no trust. Moreover, we come to a solution where Mainchain doesn't know, Mainchain knows nothing about structure of sidechain. So we built our solution based on zk-SNARK cross-chain transfer protocol. Mainchain doesn't know anything about consensus protocols that are used in sidechains. So we have Mainchain. Sidechain can run some BFT protocol, can run proof of stake protocol, can run some another proof of work protocol. It has no matter for the Mainchain. Mainchain provides security guarantees for coins that were transferred from Mainchain to such sidechains. So solution and security is efficiently verifiable. We have enough well scalability. According to current benchmarks, they are not full yet, but they are done by the Horizen team. There can be support from tens to hundreds of independent sidechains. Solution provides security guarantees. And these security guarantees are enough strong. Even if there is a case when sidechain fully controlled by an attacker, then attacker fully controls consensus, fully controls block producing, tries to organize double spend attacks or something like that. Mainchain guarantees security of coins that were moved to sidechain and then got back from this sidechain. So even fully controlled sidechain, attacker cannot steal Mainchain coins that were moved to sidechain. Moreover, if there is a censorship-resistant attack, when attacker controls this sidechain and he doesn't include honest user transaction in the sidechain, even in this case, coins can be taken back to the main chain. Moreover, if there is a case for cease sidechain, or so sidechain is dead, no blocks produced, users can take their coins from the sidechain to the main chain. And everything of this having no any trusted parties. Okay, so if we look to regular operation, when attacker doesn't have some majority or doesn't have enough power resources to take control over the sidechain, what do we have here? Mainchain doesn't track sidechain. Mainchain doesn't track them at all. Sidechain must track the mainchain. Coins are sent from mainchain to a sidechain, processed in the sidechain, or sidechain exchange coins within the sidechain, and some amount is sent back. So, and we have two operations, forward transfers and backward transfers. So we have mainchain. From main chain, users move coins to sidechain at any moment they want. They do some operations, some coin exchange on sidechain. And within given period of time, which is called an epoch, information on coins that are transferred back from sidechain to main chain are are provided into main chain, and these coins become available in the main chain again. So coins from here were moved here, processed, exchanged, and so on. New owners of coins moved their coin back to the main chain. This is a regular operation. So for forward transfers, this is transactions that are included in the main chain block. Main chain coins are sent to special account. So technically they are just burned in the main chain. They become unavailable in the main chain. But having proof that coins were burnt in the main chain, owner of such coin can provide proofs that he owned such burnt coin, and he claim tokens in the sidechain, and to do operations with these tokens in the sidechains. Sidechains must follow main chain, and the sidechains are always aware of such forward transfers. Backward transfers. They are initiated in sidechain. Someone says, okay, I have such sidechain tokens, I need to get them back into the main chain. And they issue special transaction on the main chains. All such requests are collected together. They are united into special structure that is called certificate or withdrawal certificate. And this certificate is provided to the main chain. And this certificate is provided regularly, and this period of time it is called an epoch. So here we have no trusted party, and main chain does not track sidechains at all. Moreover, main chain doesn't know anything on the structure of sidechains. It even can be some centralized type of database or something like that. We don't put any limitations on that. We provide security guarantees in any situation. How do we get such functionality? We provide it using zk-SNARKs. So succinct argument of knowledge using zero knowledge protocols. So we provide succinct proofs, and with this SNARK we can very easily validate all transactions within the whole epoch. So we have some state of sidechain, we apply transaction, and this state of sidechain is changed. We apply the next transaction, and the state of sidechains is also changed. All these changes within one block or within one state change can be described with SNARK. Several SNARKs can be united using recursive SNARKs together, and we have for all transactions within one block we can have only one SNARK that is very easily verifiable. Of course, it requires enough significant effort to generate, but it can be very easily verified. Moreover, SNARKs of all blocks within one epoch can also be merged into one SNARK. And within one SNARK, all transaction within the given epoch can be very, very easily verified. So a similar approach, moreover, they were authors of this idea, was used by the CODA protocol, but they use this approach for main chain. We apply this approach for sidechains. Okay, so each sidechain has its own specific SNARK verification key and special proving scheme that reflects rules of the specific sidechains. So as a result, we have that sidechain logic is fully independent from main chain logic. Moreover, main chain should not know anything about sidechain. Main chain knows only such verification key, SNARK verification key, and that's enough to provide security. So what interaction do we have here? So we have withdrawal epochs, we have main chain. Within main chain, at any given moment, with forward transfers, coins are moved from main chain to side chain. They are processed within sidechain, and within this period, some users would like to move their coin back from sidechain to the main chain. And here it is all such transactions are united into withdrawal certificate, and withdrawal certificate is provided to the main chain. And these epochs are sequential, and with the length of this epoch, we have the liveness period. So each transaction that is intended to move coins from sidechain to main chain will be definitely processed within withdrawal epoch. So if we go to the fully fledged operation, when we take into account malicious actor and powerful malicious actor, what additional features do we need to have here? Of course, we need to have some withdrawal safeguard. A sidechain cannot become a source of infinite source of tokens. From using this safeguard, we guarantee that no more coins will appear in main chain than it was sent to the sidechain. Even in case, in the very unlikely case that there is some very serious mathematical mistake in circuit, zero knowledge circuit, even in this case, main chain remains secure. Besides that, we need to introduce such parameter which is called withdrawal certificate quality. What it means? It means we don't know about from on the main chain side. We know nothing about consensus protocol, but in any case, it can be decentralized, and we expect they are decentralized. And within the decentralized system, we can have forks and so on. There can be several certificates that are valid. And among, because there are two chains, one longer, one shorter, but both chains were generated by some set of participants, of consensus participants of sidechain. And if there are forks in the sidechain, we need to select the longest chain. We need to follow the longest chain rule. And to enforce this rule for the sidechain, we use the parameter which is called certificate quality. With this parameter, we guarantee that the longest chain, if there are any chains in sidechain, so the longest chain will be taken to the main chain. And we have two extra types of main chain withdrawals. We call them main chain managed withdrawals. Backward transfer request and seed sidechain withdrawal. What does it mean? It means that if there are malicious majority in the sidechain, if there are some censorship attack and so on, and withdrawal transaction backward transfers are not processed in the sidechain, then user in the main chain initiate a backward transfer request. Of course, they pay more fee, but this transaction guarantee that if they own some coins in the sidechain, these coins will be moved back to the main chain. It doesn't matter whether a user sent these coins to the sidechain by himself, or he got these coins in the sidechain during some exchange or something like that. But in any case, he can initiate such transaction in the main chain and get his coin back from main chain, not depending on the situation in the side chain, whether it is maliciously controlled or something like that. If sidechain becomes dead, we call this a cease sidechain withdrawal. No blocks are produced, nobody can send the certificate. In this case, if user has some coins in the sidechain, he can use such a feature which is called cease sidechain withdrawal, and in this case, he gets his coin back. So there is no need to have some watchtowers that watch sidechain if something goes wrong, to take coins as far as possible to the main chain and so on. You can send coins to the sidechain, and in a year or in a few months, remember about that, even if sidechain is not functioning at all for a very long time, you definitely can get your coins back. And of course, there is a feature which is needed to bootstrap sidechains. So, backward transfer request, how it works. we have main chain. In the main chain, backward transfer request appears. After that, sidechain must process all transactions, both forward transfer and backward transfer request, and they will be reflected in the withdrawal certificate. So coins will appear, or if this backward transfer request is incorrect, there will be proofs that this request is incorrect. But in any case, it guarantees that with no dependence what happens here, main chain coin holders can get their tokens, can get their coins back in the main chain. So for bootstrapping sidechain, what do we need? We need to specify ledger ID, a number of specific sidechain. We need to define start block from which main chain block we started our sidechain. We define epoch lane. This is liveness parameter within which period of time users definitely get their coins back from sidechain to main chain. It can be 1 hour or several days or longer. It depends on specific epoch lanes. We have submit lane. This is also a liveness parameter for submitting a certificate. And we have some verification keys and some other service data, which is needed to run this sidechain. So from main chain, situation is quite simple. We need to process bootstrapping of sidechain. We need to understand forward transfer, withdrawal certificate, and two extra operations that we don't need in normal case, but to provide security guarantees. That's all. We don't need to know smart contracts. We don't need to know forks. We don't need to know consensus. We don't need to know anything. We have only these very simple operations that are provided with SNARKs, with SNARK verification. Okay. Zendoo is just general protocol, and its institution is a lattice sidechain. It is a decentralized permissionless blockchain. It is a simple ledger of payment of transactions that does not possess its own native asset. So it processes only main chain coins. It is based on proof of stake consensus protocol. It is based on Ouroboros. And we assume that main chain is a classical proof of work blockchain that run is Nakamoto consensus. So lattice is developed for Horizen Mainchain, and such sidechains will be deployed with Horizen Mainchain. Okay, if we are speaking about Ouroboros family proof of stake consensus, we have epoch. We have some epoch that unites some sequence of blocks. We have slot some period of time to produce a block. We have slot leaders, participants, stakeholders who are entitled to produce a block within given period of time. And we have slot leader selection procedure. Depending on this selection procedure, we can have Ouroboros Classic, we can have Ouroboros Praus, Genesis, and some other Ouroboros family protocols. And sidechain is run, lattice sidechain is run using this Ouroboros consensus. Sidechain follow the longest main chain branch. We include block references. So we have main chain, and inside chain we include references to main chain blocks, and thus we bound our sidechain to the main chain. Moreover, such mechanism guarantees that all main chain transactions, as like forward transfer or some another emergency type of transaction, will be included into the sidechain and will be processed in the sidechain, and they will definitely appear in the certificate. And here we also rely on persistence and liveness properties of the main chain. So we provide security guarantees, but we provide security guarantees within the main chain. Of course, it's very hard, even if possible, to make sidechain more secure than the main chain. Okay, that's the main ideas. And what further research directions do we have right now? First of all, it's incentive scheme. It should be balanced. We should have equilibrium. Moreover, this equilibrium should be stable, and the system must automatically return to this equilibrium if it's shifted in some case. And we have many participants. Of course, there are sidechain users who transfer coin to sidechain and exchange coins in this sidechain and pay fees for that. And using such funds that are provided by sidechain users, we need to incentivize Mainchain miners to include sidechain transactions, as we discussed, like forward transfers and backward transfers, and within withdrawal certificate. We need to incentivize sidechain block forgers to produce new blocks and to avoid forks. We have extra service providers because we have SNARK generation that is computationally heavy, and there is needed some heavy computational resources to generate SNARK, and we need to do it in fully decentralized way, not involving something like Amazon Cloud or Google Cloud or Microsoft Azure or some DigitalOcean or something like that. We need to have full decentralization. Of course, we need to think about developers of sidechain, because there is a lot of code to develop and a lot of work with creating some proof scheme and so on. They also need to be incentivized. And currently we are working for incentive scheme that provides all this balance. So our next paper will be on this incentive scheme. And of course, we need to think about advanced security model for real-world deployment. So, of course, we currently rely, as all the rest sidechain developers, to the persistence and liveness of the main chain. So, if we reached some point, and after this point we have necessary amount of confirmation blocks, in this case, we consider that this part of blockchain is immutable. This is true for very many cryptocurrencies, but if we look for some examples like for Ethereum Classic, for last few months, we can see that there were a lot of risks, and they have forks that have very long lengths. So they have lengths of, as far as I remember correctly, over 4,000 blocks. And in this case, we cannot rely on persistence, and in this case, what problem can happen? We rely on persistence. To provide liveness, we issue this withdrawal certificate, and if very long fork happens, it means all sidechains will be considered dead. Of course, it's not normal situation, but such situation breaks all security model, but we need to go further. We need to go over these security limitations, and currently we also work on advanced security model that allows to keep sidechain alive, to provide security guarantees even within the case when some forks happen even in the main chain. So we provide lower security requirements for the main chain, but we also keep our security guarantees for the sidechain. So that's all about our model. Thank you, and I'm ready to answer your questions.
What is the certificate? Like, how often does it have to be submitted to the main chain?
So we have this liveness parameter. This liveness parameter, and within one epoch, within one withdrawal epoch, this certificate is provided. And this certificate is needed to be provided within epoch. If certificate is not provided, then sidechain is considered dead. It is considered seized, and only these seized transactions can be used to take coins back from this sidechain to the main chain. This is a parameter. This is a parameter of the system epoch len and submin len. Within this period of time, certificate should be submitted. So it can be submitted within 1 hour or within 1 month. It's a decision of sidechain developer. So With such certificate, we guarantee that coins from the sidechain appear in the main chain. Of course, it's better to have this period as short as we want, but having some heavy computational effort needed to generate such certificate, it's technically better to have it at least 1 hour. But in any case, this parameter can vary.
But was it by the nature, like, is it just like a small proof, like how long is it, like the size wise, I mean?
So the size of certificate, how much blockchain space it takes, yeah? It depends, size depends. Size depends on sidechain capacity. So it can be hundreds of kilobytes, it can be less, or it can be more. But it is provided enough array, so if hundreds of kilobytes is provided within several hours, it's quite acceptable.
So how to manage the case when the gas price skyrockets and submitting a certificate costs you like, I don't know, $100 and you need to submit it like every hour? How do you manage the economy of this procedure?
Great question. We work on that. It seems we have a solution. So we have extra service providers for certificate validation and submission. So we have flexible schema on that. We have not come to the final solution yet, but we have approaches to solve this problem.
So basically, like, the developer of the sidechain donates their money to submit their or how is it?
It's one of possible solution when someone who wants this sidechain to keep alive, he can donate to this sidechain. Yes, but besides that, so here we can have some centralization risk because sidechain relies on these donations. We also have some alternative solutions that allows us to have fully decentralized. We have a special incentive mechanism that allows us to get equilibrium. If gas price or transaction fees becomes too high, if submission becomes too expensive, in this case there will be automatically a shift of funds distribution. Later it will also will be reflected in transaction fees in the sidechain, or sidechain users will pay for that, but we will reach equilibrium on that. And
so basically the users at the end of the day are gonna pay for the submission of the certificate?
Maybe not at the end of the day, but...
I mean, like at the end of the story, I mean...
Yes, so we have some general fund which is collected from users, so which is filled from transaction fees from users who use sidechain. So we have sidechain users. And who is incentivized with which priority, it is taken here, and here we have some equilibrium. Maybe we can pay less to block forgers, for example, to have less stake participation and so on. But here we keep sidechain alive. When transaction fees goes down, in this case, block forger reward will be increased. We return to the normal state. But for this rare case when we need to pay much more for certificate submission, in this case we will have funds, and they are managed in decentralized way. Great. Yeah.
Okay, the last question. Sorry,
it's
taking too long. How do you deal with the case when, for example, on the sidechain, the validators are malicious and they change account state by themselves? For example, they issued like extra coins for their account and then they issue the withdrawal. How is it managed, like, by the ZKs?
Everything is handled with SNARKs. So they cannot mint new coins in the sidechain. New coins cannot appear in sidechain at all. Coins can appear only from forward transfers. Someone moves their coins from main chain to sidechain, and they have their private keys to sign these transactions. These private keys are also used in the sidechain, and this private key, corresponding public key, are known to the main chain. And all of that is compressed in SNARK verification.
Does it work with smart contracts on sidechain?
Currently not.
Okay, now it makes sense.
Yeah, thanks a lot. Are there any potential problems with toxic waste? in your approach, and have you already looked at different scams that don't use a trusted setup?
Are there any potential problems with?
With toxic waste, with zk-SNARKs. When we have a trusted setup, and it potentially can provide the way for attacker.
Great questions. Currently in our model, we have assumptions that we have ways for secure ceremony for establishing our scheme. So in general, it may lead to some problem if in the very beginning with sidechain deployment there will be some private information that was not destroyed. But if you look to current approaches like Hello or other approaches, so community works in this direction, and there are approaches to solve this problem.
Thank you.
Thank you.
How do you ensure that when funds are returned to the main chain, that they're locked on the sidechain? In my vision, there should be the certificate you generate. It should be kind of submitted to the sidechain, and the main chain should verify that there is a certificate on the sidechain that basically the funds are locked on the sidechain, which would mean that the main chain would need to know about the sidechain, but you said it shouldn't. So how do you solve this if it shouldn't?
So the question is, how do we differentiate funds from one sidechain to another sidechain?
No, how do you make sure that the main chain, when the funds are returned, that they're locked on the sidechain? Because the main chain cannot operate them unless they're locked on the sidechain. So
in the main chain, we have forward transfer. This forward transfer is done using private key. And public key corresponding to this transfer are known to main chain. So private key is also used to move funds in sidechain. So main chain knows initial public keys here. And after that, we have a sequence of transactions that are described by SNARK. And the SNARK also describes the final certificate. So here we have such transition of states, and they are very complex. They are described in a very compact way in this certificate. You may also ask in Russian, for example.
Yeah. I'm thinking what you said, and yeah, I definitely have more questions. So you knew on the main chain, you have to ensure that the tokens are burned there, because for example, let's say that someone generated a certificate and the certificate just sidechain doesn't know about it. It's kind of a fork of a sidechain.
So your question, do I understand your question correctly, that we have some double spend here?
Yeah, on this double spend on the sidechain, because the sidechain doesn't know that return has happened. Because someone made a return, someone generated a certificate, right? But he didn't submit it to other networks, so now he has certificate, but the sidechain still, if there is no record on the sidechain that the funds are, if there is no confirmation from the main chain that funds are really burned on the sidechain, then sidechain can have a fork, right?
So what do we have here? We have such withdrawal request. And these withdrawal requests are consistent with all ledger history here. And this ledger history is put into the certificate. It is using a correct scheme. It is impossible to generate a certificate which has conflicting transactions. There can be only 2 conflicting certificates. So, and main chain will choose only one of conflicting certificates. And I mentioned about certificate quality parameter. And based on the certificate quality parameter, main chain selects the certificate which belongs to the longest chain.
So suppose there's a rollback on the sidechain because someone generated a few blocks and didn't share it with anyone. So you come back to, the sidechain comes back to the moment where there's no withdrawal request and it continues to operate the money. However, the fork that returned the money to the main chain, now the main chain operates the same money. So what would happen to that sidechain?
Okay, so we have here certificate and sidechains here is fixed. So we have this certificate accepted here, and sidechain cannot fork from here and provide this correct certificate. Sidechain, if this certificate is accepted in the main chain, sidechain must continue from here. They cannot continue from here. This certificate from this fork will not be accepted. And if this certificate will not be provided, in this case, sidechain is dead.
I see. I see. So does it mean that if all the sidechain blocks till the moment when certificate is submitted is lost, you can still continue just from the certificate on the sidechain?
If you are within epoch, you can continue.
I mean, suppose I lost all the blocks till the moment the first certificate is submitted, so they're all lost. Can I continue the sidechain from the second epoch only with the main chain?
Okay, this certificate is submitted. This certificate is not submitted yet, and we were at this point, but all these blocks were lost for some reason, yeah?
No. I mean the other situation. So you submitted the certificate, right? So this block is okay on the main chain, but now you lose all those 5 on the side chain, and you have to make the epoch 2 on the side chain, but you don't know the epoch 1. So is it possible to recover the side chain from that?
So you're speaking about one participant or the whole network?
I'm saying about the sidechain. Can sidechain, because when sidechain submitted something to the main chain, this submission, the whole epoch can be faked. I mean, it's not kind of faked. It's just the type of attack when you generate an epoch and you don't share it with anyone. So you submit it to the main chain, and now all this epoch is basically lost. So you can break the sidechains because it will be now stopped because you submitted the epoch that no one knows about. People only know with the certificate on the main chain that the epoch has happened, but I don't know what had exactly happened. I only have the certificate. So can I continue on the sidechain from that or no?
Okay, so I can continue this question in several directions, so I will give a reply in these several directions. First of all, we are a block forger in the sidechain. We have some problem with our PC or something like that. We lost everything, but in this case, when if we are within the same epoch or even later, we are in the decentralized environment in the sidechain. We just synchronize to the state in the sidechain. That's no problem for a single participant. If there is some censorship-resistant attack, for example, censorship attack. There are block forgers. They are all malicious. They produce blocks. They don't share these blocks with anyone else. They don't share state with anyone else, but they continue to submit this certificate. So state here is known to users. State here doesn't know to users at all. Even valid certificates are submitted. Yes, we also take this situation into consideration. So if we are a user, we can send coins to the sidechain. After that, we disconnect from the network. We disconnect it for a month, for several months. We don't need to track the sidechain state. In any case, we can get our coins back. If it is normal operation, we just use our normal withdrawal request. If there is some censorship attack, we will use a Mainchain management request. We also consider this.